Welcome back. Before we start with Module 4, we will have to talk about raster data. Yeah, raster data. So for raster data, and we did animation. So we did 3D and we did network analysis, data mining, not a lot, proximity analysis we did, like buffering, animation, yeah, for sure. So it was the Pittsburgh we fly through. Okay, so we will jump in. So the objectives here, we will learn different raster analysis functions and techniques. So and the techniques. So here it should be and functions and techniques. Okay, and then we will understanding the raster model and storage for raster in ArcGIS. So yeah, we will talk about a lot of raster data and the analysis and geoprocessing and the environment. So we already did that. So when we did the environment settings for the project, I could do a screenshot and put it in my slides. So we did the extent in ArcGIS Pro. So it depends what version I'm gonna use to show. But now I have old version and mixed version. So my slides are kind of not updated yet, but it's okay. Alright, so now why do we use rasters? So because raster data are better storing certain kinds of data and better at analyzing kinds of data. Often faster analysis than vectors. So it just depends. So here it mentioned faster. You just have to depends. You store. It will take a lot of space. Some vector data it will be faster. So I'm not quite sure for quite agree on here. So the data right now, it's unless you are dealing with big data, it's not a huge thing here. Okay, and often faster analysis than vectors. Imagery desirable for certain maps, but here the coordinate precision generally lower, and high precision has high storage costs, so that's a trade-off, and cannot store multiple attributes. So that was the issue. So now let's review the vector data. So for vector data, we have a points, lines, and polygons best representing the discrete features. So like here, points, lines, and polygons, so that we have an empty space. Polygon, you can, unless you cover the whole thing. So, but for raster, it's a graphic image, so the whole thing, the gray color is the whole thing. So now graphic image best representing the continuous features. So the discrete and versus fields. The discrete object view, it represents the world as objects. So with well-defined boundaries. So like you have a border and an empty space. And the field view represents the real world as a finite number of variables, each one defined at each possible position. So there are strong association between the raster and fields and vector discrete objects. So let's look at here. So the discrete objects versus field view of the world. So for points, you can see the points here and lines. Yep, lines that's we represent, and this is polygons. But for continuous surface, we kind of use as a cells, and then using the coordinates that we do not just separate. It's the whole surface. Okay. And field representations in a GIS regularly placed sample points and irregular placed sample points, or rectangle cells, irregular shaped polygons, the triangulated irregular network we call team, and then polygon contours. So let's look in detail. So the rectangular cell or grid representation. So a grid defines that the geographic space is a matrix of identically sized square cells, and each cell holds a numeric value that measures a geographic attribute, like elevation for that unit of space. So for the type of fields, we will have a scalar field having a single non-directional value, land cover type, and elevation. Vector value at every point. For example, we have a direction and magnitude, or just a direction. So land, surface, gradient, slope, and aspect. Wind, we have a direction and magnitude. So we will demonstrate later. I'm linking here. So the definition for a grid, so that we will have the upper left, and upper right. So the cell size, and here we could contain no data. So number of rows, we go up. So row 1, row 2. Excuse me. Excuse me. All right. Sorry. That we have, just like Excel, that for a row we do the horizontal for row, and for the column, and then on the lower right hand side we'll have the x and y value. The spatial game, the resolution defined by dimensions of grid cell. Grid values can be in form of floating points and decimal data, or integers. So integers. So the floating point grid, so right here, so continuous data surface using floating points or decimal numbers. So like here. So, and this is the 30-meter dm, or the 1 arcsecond net. So 2 meters dm from LiDAR, or approximately 1/9 arcsecond net. And so for the intergrid value attribute table, so the tree type grid, so the tree type, so that we have the value here, and 1, 2, 3, and count, so that value 1 means this is maple. So here all it's maple, and we use a code, and we have maybe we have a 6 maples, and then we have an oak, that 23 oaks, or 8 pine trees. So attribute of grid zones. So maybe might not, maybe the 1 cell doesn't mean that it is, it doesn't mean it is just one tree. So it's just a zone that we could now, this area we have 8 cells that could be pine tree. So points as cells. So that point, we can have a point as cells that how represent like this, and point as lines. So a line, a monitor here. So in general, that like 5 to 5 grid. So we can have 7 points, and then here 10 to 10 we have a 14 points, and that, for example, we want to represent network roads. So the 20 times 20 grid, we could have 21 points. So, and the polygon zones that we could represent here using the vector converter to raster. Okay, so what is raster, and what is raster data model? So, as I mentioned earlier, that we have XY location. Remember the upper left and lower right. So this cell we can fix into the georeference to Earth surface. So the XY location here. So the pixels or cells. So each pixel contains one numeric value, and the dimension of a pixel varies. The resolution and the value represents some property of that pixel area. And for example, we could do is elevation or rainfall. And the value may be integers or floating point numbers. So here, unlike polygon, each cell has only one attribute. It's value storing multiple values means storing multiple rasters. So, and the data set they use is the binary data. Most raster formats use binary storage, and numbers are stored as a series of zeros and ones, representing numbers in base 2. So binary values are grouped by 8. So and the pixel depth, okay, let's look at the pixel depth. That the number of bytes used for each pixel. So when we have a more pixel, we have large numbers and more space. So integer values, 11 bit pixel, 1 byte. We stored is 0 to 255, and 16-bit pixel, 2 bytes, stored 0 to 65,565, and 24-bit pixel we have is 3 bytes and stores 0 to 16.7 million. And the floating point values that required for decimal numbers, okay, for decimal numbers. Decimal numbers storage and 32-bit pixel, and we also have 3-bit pixel for bytes, okay. And types of raster data that we're gonna go over. So the analysis functions that, let's see, okay, all right. So the analysis functions available for raster number in the numbers and include various sophisticated applications. So here we will introduce some basic concept and analysis functions, but the topic spans a much greater breadth of theory and techniques than we have time to explore. So the raster analysis has plenty of additional material in the software documents for spatial analysis. So the spatial data can mean to 2 forms, okay? And the first one is discrete. Data such as soil types or land use represent spatial objects and from distinct objects or regions on the map. So soil, okay, and continuous data right here. Continuous data. This is DMM. Continuous data such as elevation may smoothly over a range of values and form a surface of field. And the vector. So the vector data model best stores discrete data. Raster easily store and analyze continuous data. So like here. So discrete raster rows, we can see it's better looking here. So the image here. And the raster properties, that the same way you right click on the layer and you go to source and you can see different things. And this is ArcMap, and right now ArcGIS Pro is the interface look different now. Okay, so here we would say like vector data, the raster have a defined coordinate system with a projection and a datum. So the raster is georeferenced by specifying the XY coordinates of the center of the upper left pixel and the cell size, the height width of the pixel. Usually pixels are square. So a 30-meter raster has pixel composed. So right here, so cell size, which is right here. It means that a 30-meter raster has pixel composed 30 to 30 meters square, and the cell size is specified in the coordinate system map units, and meters or feet are typically used. So although one can store a raster in a GCS, so let's see, what is the coordinate dimension here? GCS. In a projection with significant distortion. So, and then here we can say source type continuous floating point, okay. Therefore, the raster data are normally stored in whatever projected coordinate system gives the best and most undistorted view of the data. And the main exception occurs for data providers such as the U.S. Geological Survey, which provide topographic or other data in GCS format, such data should be projected before they are used. Okay, the bands. Let's look at the bands. So a single raster may include multiple arrays right here. So most often used to store color images and satellite images. So the raster resolution, it measured by the cell size dimension. Storage space increases as the square of the resolution. So vector format, this is the 200-meter raster, and 50-meter raster 16 times bigger. So we can see that it's more defined. Cell size unit. So that when we right click on it, we can see the cell size unit. The cell X and Y resolution units are based on the raster coordinate definition. So decimal degrees. So we will usually see the decimal degrees, meters, or feet. Because the distances and areas are fundamental to raster analysis, it's best to use projected coordinate system for rasters. So when we are on the exercises, we can link back on that when we are working on it. Some of the common raster data. The first one is digital elevation model. 7.5 minutes, which is 30 meters spacing. DOQQ digital ortho photograph quad era photograph with map quantities and ortho rectification. So the digital raster graphics that scanned and georeferenced USGS 7.5 minutes, that is 1 to 24,000 topographic sheet. Okay, let's look at some of the example that we have a 30 meters, 10 meters, and 5 meters, and 2 meters, and 1 meter. So we can see that the resolution, that it's just like it's a trade-off. You want to get it in detail, that you have to zoom in. So larger scale is right here, and smaller scale that you can see maybe the whole part of Manhattan, and then here you only see just one building. Okay. And satellite imagery, we will go into detail. So those are the satellites that we need to remember or be familiar. So this is the Landsat. It's right now it's in operative November 2011, and Landsat scanline era in May 2003. So there was some issue in Landsat, launched February 2013. AVHR are a lot of people using this advanced very high resolution radiometer, and MODIS, moderate resolution imaging spectral radiometer, and SPOT is a French satellite, and this Iconos, private owned and operated. So they do provide nice information, but you do have to spend money to buy on it. Okay, to buy. So images and grids is a native raster format, and images we will have the format including TIFF and BMP and SEED, Mr. SEED, and JPEG. So usually we deal with it's more JPEG, image, ADOS use a lot. So I do use ADOS. So we will talk about TIFF in maybe in detail, maybe in some sessions. We will see. Okay. So for the raster property, when you go right click on it, we did data source, type of file, and location. Where is the data? You can see the source and raster information about the pixel. So I usually don't check. That's not good. So I always have to come back to check. And here extent, that's just like when we produce the San Diego, we created the density the point density maps, and we do use the extent, which is the top, bottom, left, and right extent. So like you can produce data within this region. Okay. Spatial reference coordinate system, and here we can see the spatial reference is NAT 1922, 1927, the UTM zone 12 north. So for these, you have to take cartography so you know what is the spatial reference. And statistics, minute and maximum and mean and the standard deviation per band. So we will talk about the remote sensing images. So for the ancillary files, so an ancillary file, AUX and AUX.xml, it stores any information that cannot be stored in the raster file itself: color map, statistics, and histogram, a pointer to the pyramids file, coordinate system, and transformation project information. Transformation, basically, it's just like you have a different scale and you transform into different scale and fit it into the map. And projection information, yep, sometimes we have to deal with that. We can do predefined. Of course, sometimes maybe some issue or the cloud when the scan images there are some issues there. So no data issue could be there. So cells or pixels that have a missing information. So sometimes no data and 0 are not the same. So 0 is a valid value. Cells do not participate in statistics calculation. Cells can be displayed specific color or transparent. So we did many times for transparent. So for the raster pyramids, so good overview, it's kind of just you reduce the resolution and based upon the original raster, so the file created, so pixel size double at each level and improves display performance. So there are some good things about it, and set a creation time adds more storage. That's really nice. Then you can store more data not used during analysis. That's nice too. Okay. Color maps, we will talk about more for the color maps. So the pseudo color map table use the display data consistently with the same colors. CLR is the extension for the file, and set of values that are associated with colors, RGB. So when we do in Windows Explorer, we can look it up, and stored as part of a raster dataset, editable, and capable of handling up to 8-bit data, 256 colors. So statistics, when we do statistics, we used in performance certain task, improved display, classifying data, and stored in an associated ancillary file created using the calculate statistic tool. So let's look at some example. So raster attribute table. We do have an attribute table for each of the cell. So it stores additional pixel information other than the pixel values, and display raster with any field with the attribute table can join to other tables. Usually we do not do like a table join for raster. That's interesting. Okay, so the raster rendering that remember we did for the San Diego, we use classified. Okay, so for the stretched we haven't used any stretch yet. So stretches value along the color ramp. Default if raster has 25 unique values. We barely use the unique values, and we use random colors for individual values. Default if raster has less than 25 unique values. So if we have more than 25, we use stretched. Unique value, we deal with less than 25. That's something we have to be aware with. And the color map. So the color map we use is pre-selected color for individual values, and default if color map is present. And the RGB. So now let's look at the RGB. So red, green, and blue composite. So it displayed each band through a different color RGB. So default if raster has greater and more than 3. So greater and equal and greater than 3 bands. Okay. For the classified. Okay. So for the classified, places ranges of pixels into separate categories, not a default renderer. I think for ArcGIS Pro, it is a default renderer. Last time we went to classified, we choose the classification from 10 to 5, and then we rename it. Okay. So raster rendering, the first is stretched. Stretch values along a color ramp so that we can see that raster has more than 25 unique values. And this is unique values uses random color for individual values. The default raster has fewer than 25 unique values. So if more, we will use stretched, okay? And the raster rendering for the color map uses pre-chosen color for individual values. We just talked about it. And see, that's the color thing. And here RGB, it displays use each band through a different color, red, green, blue, and default is raster has 3 or more bands. So the raster rendering classified places ranges of pixel values into separate categories, not a default renderer. Okay, alright, so we're done talking about the first section of that, and we will continue and we will do a summary for our raster data because we just started it, and we talk about how would you what kind of data is raster data. Oh, no, I need to start from the beginning. What kind of data is raster data model, and how would you store it, and how would you present it, and the method that when you scroll down to represent the data and different methods, and we went through each method. Okay, so now in this part, we're going to talk about is raster analysis. So for raster analysis, it uses cell-by-cell function. So on one or more input grids. So like here, if we have input, we could have output. So the cells must be the same size and line up spatially. And older software require the user to ensure that all input raster had exactly the same size, shape, and aligned cell sizes. So now, even for me, I don't really check. Okay, let's back up a little bit to review a little bit about raster analysis, the geoprocessing. So, the vector. So the vector, we had buffer and overlay. We did union, intersect, merge, and manipulation, and we also have the clip, erase, append, and dissolve, etc. For raster data, there are some similarities. There are some differences. So because the vector analysis, so it's a little different for the raster analysis. Some parts are the same, but they might have a different name. There are some shared similarities, and something are different. Okay, all right. So we will go over some key things. So here we will talk about the distance and then measurement function, and we will talk about local operations. So and then neighborhood operation, zonal operation, and some of extract and resample and cut things, and conversion, reclassification, and stuff there. So that's what we're gonna went through. So if you look at raster analysis techniques, it will include the spatial analysis. That for raster we will have distance function, density function. We already did density function, interpolation, not yet. Surface function and neighborhood function and zonal function, classification, resampling, and conversion. So we might be able to do some exercises along the way. I think we already did. The only thing is for zonal. And actually, and more stuff we will talk about here. We might not be able to cover everything. Hopefully we can over the coursework, and I might have some new material that we can do more. But after this book, the spatial analysis, I think I'm good with ArcGIS Pro, and what I'm gonna do is that there is an online course from Israel, and we will jump in that. I think it starts April 18th, and after that, we will do I think we're gonna do is just Python, back in Python, and then SQL, and then back in ArcGIS Pro again. Okay, so the distance measurements, so physical distance, okay, measures distance by summing links between cells and multiple sum by link length, and lateral link we have a 1-point cell, and diagonal link it's just math. Then when you do it's just square root 2, which is around 1.4142 cells. Okay. And variation of location, closest source, and relative cost distance. So let's look at some examples. So the distance function calculates a continuous range of distance from a specified set of objects. So, and we could have least path between 2 points, buffers, and straight line distance. So for the Euclidean distance, the Euclidean distance function produces a raster in which each cell reports the shortest from a set of specific objects, such as rows. So here, distance to rows meters. So it starts from a set of features, points, lines, or polygons. It creates a grid where each cell represents distance to the closest of the features, and the distance are given in coordinate system map units. Okay, so then we will have to do is the Euclidean direction. So for the Euclidean direction, that we could see that it calculates like the row direction here. -1 flat, or north, northeast, east, southeast, south. The different color coded, and we can know its direction, how it's facing, and often created in association with a distance function. It indicates direction of travel to the closest road. So for buffers, we already did many times. So logical expression easily create Boolean raster representing buffers from distance rasters. So in the lowest cost path, we haven't done anything yet, but I'm going to show some material and maybe some data for that. So there are 4 steps, so as showing here. So the cost distance function consider more complex and flexible approaches to travel. So consider a mountain with 2 points in opposite sides, and the shortest path to the opposite point goes over the mountain. However, it is easier to go around the base, even though the base is longer due to the effort cost of climbing over the mountain. Slope is one kind of cost. Heavy vegetation, marshes, and off-limits area are other factors that increase the cost of travel. So in a cost distance analysis, a raster is first prepared and estimates the cost of travel over a surface. A single cost factor such as slope could be used, or the raster cloud combined different types of costs, and this cost raster is used to develop cost direction raster, which tells a traveler which direction incur the least cost, and a cost accumulation raster to keep track of the total effort expended as the traveler moves. And this raster can be combined to calculate the least cost path between 2 points, so indicating the easiest journey raster than the shortest. Here, a slope raster was used to designate the cost, and a least cost hiking trail was calculated. Okay, so here is an example that from a university they did for in Kansas. So this has got the concept period, and then you can see they calculate the Euclidean. This is not they did a location, they assign things here. It's a little difference there, and then they combine 3 things together, and you can see distance measures, Euclidean direction. They also did that, and cost distance, and they can calculate the cost distance measurements. So as I mentioned there, so here 1, and then if you combine 1.5, 3.51, divided by the cost effective that you put in the formula. 1 plus 2 is 3. 3 divided by 2 is 1.5. 1 divided by 1. We got 3 here. 3 divided by 2 is 1.5. 1 divided by 1.5. 1 times, not divide, times is 1.5. So here we have this side, okay, this side, and we will have a 1 plus 5. 1 plus 5, and then divided by 2. So you even it out. So 1 plus 2 divided by 2. So you even it out, and you times 1, and then this one you times 1.25. So for this direction, okay. So, and the cost distance measurements. So the source cells and the cost grid and the cost distance, and they calculate the distance and the shortest path. Then you get a number, and then you get the cost black link. Sometimes you have to put a file for the cost black link to find the neighborhood that is the next cell on the least accumulated cost path to the nearest source. So then they get the least path, and from point A to point B, that you put a lot of physical geography features so that you get this. Okay, so let's move to density functions. So our client data, we did use the density function, which creates a raster showing the frequency of objects within a search radius specified by the user, and the function visits each cell of the output raster, so counts the point cities falling inside the search radius centered on the cell and assigns the count to the cell. So if an attribute field is specified, the counts are weighted by the attribute. And now here it shows a point density map of a city population in the United States. So you can see where are the populations are. So distributed. And we can see that within attribute, the function would count the number of cities. With the attribute, it counts the number of people, and the counts are given per unit area, as in people per square mile or cities per square kilometer. A larger search radius products a smoother map, but will show less detail than a small radius. And with choosing this research radius can take some experimentation, but it should be large enough so that every cell will have at least one feature within the search radius to meet this condition. A radius of several hundred miles would be required because of the low number of cities in the mountain subregion. Okay, so and then here it shows a line density function counts line occurrences within the circle instead of points, and it weights them by length and optionally by attribute. And this function could be used to calculate road density within a national forest. National forest attribute field might be stronger weights to primary roads and a lesser weight to primitive roads. Okay, so now we can see that our large radius gives smoother results. Large radius gives smoother results, while the radius is giving a map units. So that the point density function assumes that the entire weight value is present at each point, but it is not always true. A city cannot have 100,000 people living in, at a single point. So like on the map, you can here it's impossible that people are all just concentrated here. It would just spread out everywhere on the map, and it just shrink down the scales. Okay, so a kernel density function spreads the population value smoothly over a circular area. So we did point density, so we didn't have any chance to to do any kernel density. So it's a raster analysis, so that this kernel density function provides a more detailed. So we have a more detailed, it provides more details, so and provides a more realistic model to the population distribution, and the resulting raster will appear smoother than the result obtained with a point density function. So the search radius value has less impact on the kernel density function, although larger radius will produce more generalized rasters. So here, the interpolation. So I did a lot of interpolation because I was working on climate data. We do use interpolation to predict some values in between measure points, but it's not like accurate. But it's better. The interpolation just use the Tobler's first law of geography. So he mentioned that things, the further you get and the more differences you will have, the closer you have more similarities. So I would say compared to Florida to Georgia, and people in Georgia, they speak, the accent will be similar, the food will be similar. And if you go to Indian or China or Iceland, then you will see a huge difference, alright? Okay, so the interpolation takes measure values at points and distribute them across a raster, estimating the value in between the measurements. So that's interpolation. So a common example involves taking precipitation measures at weather stations to create a continuous precipitation surface map. But a lot of people don't like it because it's very interesting if you create a map like this, and then the farmers say, well, I got my gauge, I got maybe 10 inches rain here, I only get 1 inches across the road. So for a lot of people, they really care the precision of the data. And even there was just some crowd, they dump maybe 10 inches here, maybe the periphery area they only just have 1 inch. And since the map, it presents at a very small scale, and people live in real world, they in a larger scale, then the conflicts between them, it's there. So now the sample point features climate stations with annual precipitation values and interpolated continuous raster of preposition values. Okay. So like I mentioned here, so the actual elevation is like this, but interpolated from summit, it will be a lot of different and might not be accurate. It's just like for example, if you have a club here and then the whole area, it's just smooth it out, and we could have a valley here, and here it could show high value for the elevation. So it does not represent the real world. Real world has more complicated landscape, topographic. So we have to be aware that out as a cartography or technician people or GIS specialist, we try to make accurate of the map, but sometimes we do have to send people in the field to collect data and understand what is the landscape there, instead of you just using some of the method to just assume something is there. So just have to be careful that the real world is more complicated than what you are doing here. So, and better you go in person. If you cannot go in person, that you could fly the UAV. Okay, the methods. Okay, interpolation assumes that nearby points are correlated. For example, they will have similar values, and 4 types of interpolation methods are available in spatial analyst. So the IDW, spline line, and Kriging trends, I think I use all of them during during my past many years of using ArcGIS. So 4 different interpolation methods are common. So as I mentioned here, the inverse distance IDW, weighted IDW spline lines, trends, and kriging. Each method uses different assumption and different means to obtain the result. Although interpolated and density maps appear similar, the functions work differently, and density functions count occurrences within a radius and divide by the area. Interpolation estimates a value for each raster cell based on nearby measurements. So more information about these 4 interpolation can be found in the help document for spatial analysis, and interpolation is a complex topic and the subject of entire thing for a lot of there are a lot of publications they use this, okay? And now we will have a GIS professionals. So GIS professionals should become familiar with this different methods in order to understand the benefits and the drawback and assumptions for each one, okay? Okay, so the surface analysis here that we have, the surface analysis includes a set of functions for calculating properties of a surface. Each has a slope and aspect. So although most commonly applied to elevation data, these functions can be used on any type of continuous raster. Using these functions on a DEM could help find an ideal location for a cabin. Let's look at those slope function. So it calculates slope of the surface based on surrounding cells and can be expressed in degrees or percent. So a slope map is showing here. This is a slope map. Slope map is showing that it used the trigonology. It's showing the steepness of the terrain could be identified sites flat enough to build on. So the trigonology, the tangent, so you use the rise. This is rise. This is run. Degrees of slope. That's the degree. So in percent of slope, we will use the rise and the run times 100. So aspect function. So an aspect map showing the compass direction of the slope. This is the azimuth angle that you have a 45, 90, 135, 180, 225, 270, and 1315, and it is showing the compass direction of the slope and could locate south-facing slides, hillsides to grab the cabin a warm southern exposure. So azimuth, this is this, and the altitude is the angle of the source above the horizon. So this is the direction of the illustration source 115 degrees by default right here. So a hill shape map, which represents the surface as though an illustration sources were shining on it, and it can help raster visualize the landforms. And that a viewshed analysis, so the viewshed analysis, which determines that parts of a surface can be seen from specific viewpoints, and it could help in choosing the site with the best view. Okay, and then cut and fill on a site. So cut and fill, that the cut and fill function calculates the differences between two input surfaces and is used for developing estimates of the amount of material to be added or removed from a building site. So I don't believe that I never used this function, but well, hopefully we will get a chance to explore that. Sorry. Okay, so the hydrologic functions, so because of my medicine, it keeps me yawning. Okay, the derived streams, so the watersheds and other hydrologic features based on analysis of a DEM that we can see here. It's really cool picture here. So the types of raster operations, so the local cell by cell, and we will talk about all these functions, and we will go over one by one. So now we're going to start with the raster spatial analysis. So the local single cell, we have a single cell just local here in neighborhood, or you could say focal. So that focal, we use slope, filter, and hillshade that we can play around with it. And the global, so the global and the entire data sets. So we kind of, for example, we have this, and we will use the maximum value to apply to everything here. And the neighborhoods, we will combine their maximum. So for example, that we have everything here, and for this 33, we will use maybe around 10. Then the maximum value is 33, and here if we have everything, we will go into detail. I will have other images to show you here. So for the local, we will give a single input, and local operation computes each cell in the output raster as a mathematical function of the cell. So here a focal can convert slope raster from a percent to degree. So this is 15%, and then we convert it to degree. So here that's how it look like. So for example, we have this is percent, 10%, 15%. This is close, so that's why we have a 15 something. Okay. And this is the example as the concept period that's they converted to from percent to degree. That's one example is single cell to single cell. And then we will talk about the local operators within multiple rasters. So for the raster overlay, composing overlay, superimposing, and grids, similar to vector-based map overlay and simple map algebra, we have a summary statistics max minimum that we did many times. In map algebra, we will talk into detail, and we can weigh them and calculate differently. And we also have the majority minority output grid with least frequent value among input grids. So the mean temperature, so that we calculate each one in the cell value in D, which is right here, is the mean calculated from the 3 rasters. So that if no data, then we just remain no data. So for example, 5 plus 1 plus 3, we will have 9. 9 divided by 3, we get 3. 2 plus 3 plus 4, we will have a 7. 7, 9. 9 divided by 3. 3 plus 2 plus 1, we have a 6. 6 divided by 2, by 3, we get 2. Okay. So then we added 2 grids together. It's just like 1 plus 1, we get 2. So we would just add the grids together. So overlay. So 0 plus 2, 2. Okay. 1 plus 1, 1 plus 0, 2. 1 plus 2, you get 3. So for example, you want to combine these. 0 means that not a tree, and 1 is tree, and 0 is not urban, and 2 is urban. And not urban no tree will be 0, okay? And no urban tree, and urban no tree, and urban tree. So that's very interesting to combine. And the raster overlay could be problematic. Let's look at the example here. So where are these trees in the urban area, where are these trees in the non-urban area? So be careful with the nominal data. So here we have a tree, okay. So maybe when we add together, we have urban, we have a tree. So and maybe you could say, well, what does 1 mean? And do we have a and here we have urban, then the number doesn't mean anything. So the nominal could be a little different and tricky here. So we were calculating summary statistics. We can do mean, and we can do a lot bit more stuff, okay? And for the And for the operation for map algebra, the example universal soil loss equation, USLE. So the Websmeyer and Smith 1978. So they create this. So A means average soil loss, R is rainfall intensity, K is the soil erodibility, and L is the slope length, and S is slope gradient, and C is the cultivation factor, and P is the practice factor. And we prepare each USLE input as a grid and multiply each input grid through local location, and output grid will be spatial estimate of estimated average soil loss. So for the neighborhood operations, neighborhood defined by distance and a directional relationship to focus cell, and we have 3 times 5, 3 times 3, 5 times 5, 7 times 5, 7 window. So for the operations, use neighborhood cell values that we could have with or without focus cell values, and assign computed value to focus cell that we could do summary statistics and majority minority variety. For variety, we have a number of different cell values in the neighborhood and filtering, convolution, moving window operations, edge enhancement, and terrain. Terrain, we already did hydrology, slope aspect, and surface curvature. So for hydrology, there is an online course from Coursera. They have the GIS course online there. And the interesting part was they do have the hydrology, because the person was working for the hydrology office, and he showed a lot of hydrology related his project in his class. So that could be a source that if you want to look more there. Okay, so the neighborhood statistics. So neighborhoods, that this is a window. We use 3 times 3. You could do 5 times 5. So the neighborhood function operates on an area of specific size and shape around a cell known as a neighborhood. So moving window passes over the raster and calculates a statistic from all the cells in the neighborhood, records the result, and moves on. Neighborhoods may have different shapes, including squares, circles, rectangles, and annually. Okay, so and then the statistical functions include that here we could have majority, minority, mean, and median, minimum, maximum, majority, and range, maximum value minus minimum value, and standard deviation, sum, and then variety. So let's look at the focal versus a block function. So the white cells indicate where no majority was found. So the two types of neighborhood functions are used: block functions and a focal function. So a focal function centers the window on a cell and called the target. It calculates the statistic for the neighborhood and assigns the value to the target cell, and then it repeats the process as the next adjacent cell, and consider a 3 times 3 cell averaging window for each target cell of the output raster. So the window then moves to the next cell. An edge cell is still evaluated, but will have fewer cells in the neighborhood, and the cell in the upper left corner has only 4 values to average the target and its 3 neighbors. A filter is another name for a focal function. So a block function moves the window such that it never to overlaps the previous window, but it produces a set of side-by-side adjacent windows that are independent of each other. And once the statistic is calculated for the window, every cell in the neighborhood receives the same value before the window moves on. Every cell is used only once, and block function can be used to resample a raster from a higher to a lower resolution, as might be needed to adopt a high resolution land cover data set for a coarse climate modeling grid. So focal, you can see in this block we just blurry those data. Okay, so now we can look at this. So a block function moves the window such that it never overlaps the previous window, but it produces a set of side-by-side adjacent windows that are independent of each other. So once the statistic is calculated for the window, every cell in the neighborhood receives the same value before the window moves on, and every cell is used only once. A block function can be used to resample a raster from a higher to a lower resolution, as might be needed to adapt a higher resolution land cover data set for a coarse climate grid. So, and we can look here the block, and it's a lot more, and then you can see the focal that overlaps. Only target cell receives the value, no overlap, and the cells block receive the output value. So that's really scary. It's just like erase things. Okay, let's look at this neighborhood focal functions. Then they calculate things input and output. So a focal function centers the window on a cell and called a target. It calculates the statistic from the neighborhoods and assigns the value to a target cell, and then it represents the process at the next adjacent cell. So consider a 3 times 3 cell average window for each target cell of the output raster. The window then moves to the next cell. An edge cell is still evaluated, but will have fewer cells in the neighborhood, and the cell in the upper left corner has only 4 values to average the target and its 3 neighborhood, and a filter is another name for a local function. Okay, so the neighborhood local mean, so smooth raster effects grow larger with increasing window size or repeated applications, good for removing noise and spurious values. So let's look at this focal majority. So this is a 5x5 majority filter, and this is after 2 passes to 5.5. You can see it's a lot coarser. Most frequent value in the neighborhood becomes the center value of the new raster. So let's summarize. It's a little difficult to compare these, so that 2 types of neighborhood functions are used. So these block values and focal point function. So the focal function centers the window on a cell called the target, and it calculates the statistic for the neighborhood and assigns the value to the target cell, and then it represents process at the next adjacent cell, and consider a 3 times 3 cell average window, and each target cell, as the algorithm finds the average of the 9 cells in the window and in the target cell of the output raster, and the window then moves to the next cell. So a block section moves the window such that it gives overlaps the previous window, and it produces a set of side-by-side adjacent windows that are independent of each other. Once the statistic is calculated for the window, every cell in the neighborhood receives the same value before the window moves on, and every cell is used only once. A block function can be used to resample a raster from a higher or to a lower resolution, as might be needed to adapt at a higher resolution land cover data set for a coarse climate modeling grid. So here it shows the difference in output between a block and a focal majority function applied to a land cover raster in both cases. So a 4 cell neighborhood containing 16 cells was used, and the statistic is the most frequent land use value found in the neighborhood, and the white output cells occurs where no majority was found, and the focal function evaluated each cell with its 15 immediate neighbors and then moves to the next adjacent cell. And the block function majority function evaluates the existing cells and then moves to the adjacent groups of sustain, both generalization and the original data set, but to a different degrees. So here, let's look again. So this is in detail. The focal statistic tool processed the input data set with overlapping neighborhoods, and the block statistic tool process data with neighborhoods that do not overlap. So it creates the first specific neighborhoods. For example, a circular neighborhood in the top left corner of the analysis window and circular neighborhood of a specific radius. It calculates the minimum bounding rectangle to determine the size of the output block. The minimum bounding rectangle it partitions the remaining area of the raster into defined blocks, and the blocks cannot overlap, and remaining area of inputs partitioned into blocks. It identifies in each block the cell locations that will be used in the block calculations. The cell locations are determined by the definition of the specific neighborhood. For example, a circular neighborhood that hits into the bounding rectangle. Cells that are included for analysis in the block are identified. It calculates the output values for each neighborhood of each block, and the resultant values are assigned to every cell location in the corresponding output blocks. Okay. That we can see from here. So for common neighborhood types, rectangle, circular, annulus, and wedge, the cell marked with an X, the focal cell, and image processing, also called spatial filtering. You can filter different shape as you want, or the one you identify. So the neighborhood operations that the calculation, the summary statistic we already mentioned, the filtering moving windows, and we can do slope and aspect and how it passes. You can manipulate here. And the same example that the one in concept period they did was applying 3x3 wedge enhanced or high pass filter. And this is the really old version for the ArcMap, and now everything changes and we do not have to deal with. But the idea was that the zonal groups and everything is here as well. So neighborhood, we spend a lot of time, and we're going to move to zonar, and of course we already covered the distances already. The zonal operations. So the single grid, the described geometry of zones, example and cover, we have the classes area, perimeter, and thickness centroid, two grids. We will input grid and zone vector and the grid to generate summary statistics. So what is a zonal function? That's a good question. So the zonal statistic function is sometimes considered another type of neighborhood function. But the neighborhoods are not a fixed size or shape. Instead, they are defined by another layer called the zonal layer. Okay, let's look at here. So a zone is a region of a raster or polygon features. So feature class that shares the same attribute. A zone might be a watershed, puzzle, or a soil type. And the attribute might be a name, category, or a unique identifier such as puzzle ID or even the table object ID. So the function gathers the cells from an input raster that fall inside each zone and calculates cell statistic for the zone. So for example, if a watershed layer defined the zone and the input raster contained slope, then zonal statistic would calculate the average slope for each watershed. And the zonal statistic functions may produce two types of output, a raster or a table. So a raster output places the calculated statistical value into every cell in the zone and the table output contains the zone attribute field plus one or more statistics for each zone. And this table could be joined to the original watershed polygons using the zone field and used to map the average slope of the watersheds. And zones need not to be contiguous like the watershed zones. So now the zonal statistic of limes. So the zonal statistic function can also assign values from a surface to line or point data, such as finding the average slope along a string section or attaching an elevation value from a DM to a layer of wells. And each line or point must have a unique name or ID value that identifies it as a distinct zone. Zonal statistic of points. So determine elevation of summits, the name of feature ID for each point. So each is unique zone, and we will calculate statistics for each point, and all statistics are the same, the elevation or the point. So two large watershed zones, area measured in square kilometers and perimeter and thickness are measured in kilometers, and the central weight of each zone is marked with an X. So okay, so this is the example for the zonal operation, and that we can see they do is they combine everything. Okay, they combine, so like focal, let's see how they combine. I have to go back a little bit, so that we have 2 plus okay, 2, so 2 plus 2, and I think they combine everything and then get yes, so this is 3 9 plus 9 plus 6 is 15 divided by 8. 6 and 3 9 plus 8 17. Oh, 17 divided by 8. Okay, that you get 2.25. Yep, 17 yeah, 17 divided by 8. Yeah, 2.25. Okay, so that's the example in Kansas that they do for the zonal operation. Okay, reclassify. So the reclassify function changes the values of a raster according to a scheme that designed by the user, such as classifying a slope map into the 3 regions of low, median, or high slope, or ranking suitability factors in a weighted overlay. And for a map with only a few values, such as land use code and user might specifically specify a new value for each code individually. Perhaps a town has annexed a nearby planning unit that used a different land use code and must convert one set of codes to another. The code 143 becomes 347, and so on. With continuous data covering a range of status such as slope, the values are typically classified into discrete number of ranges. So resampling. After georeferencing, output grids may have a different cell size, orientation, and location compared to the input image. Resampling is the process of determining new values for output pixel after transformation. So the resampling, that is the process of determining new values for output pixels after transformation and changing the pixel size resolution in a raster image. So often raster must be converted to a raster with a different cell size, and this processing is called resampling. So different sizes, and users may sample purposefully in order to align rasters with each other or to decrease the resolution of a data set. Resampling must occur anytime two rasters with different cell sizes are analyzed together. Even if the raster have the same size, the cell rasters might not be aligned with each other, requiring that resampling occur. And here is an example of resampling. The cell centers on the left are being transformed from coordinate system x1, y1 to a slightly larger one, x2, y2, introducing gaps between the cells and the cell grid for the new coordinate system is shown in the output by the black lines, and the cells may be resampled to the new cell using one of the three methods. So, a nearest neighbor resampling the new cell is giving the value of the old cell that falls at or closest to the center of the new cell and assigns the value of the nearest pixel to the new pixel location. The binary resampling, a distance-weighted average is taken from the four nearest cell centers, assigns the average value of the four nearest pixels to the new pixel location. And the cubic convolution resampling method determines a new value by a curve fit through the nearest 16 cell centers, assigns the average value of the 16 nearest pixels to the new pixel location, and the nearest neighbors. That is the farthest method that should always be used in category raster data. The binary method is the best to continuous raster like elevation. So this is something we have to remember, okay? Okay, so here the block neighborhood function provides a alternative resampling method that is more flexible than the three standard strategy because different types of statistics can be used. Okay, so there is a majority statistic was used to find the most frequent land cover values in the block, which provides a better estimate of region's content than using the value at the center of the block. Although this is not an option for automatic resampling, it can be helpful when a user needs to coarsen raster data and wants to do it using the best possible method. Okay, so the caution that I want to mention here, resampling can degrade the quality of the data set. Best practices dictate that the user retain full awareness of the coordinate system and cell sizes of all input layer being used for analysis and endeavor to standardize them before processing occurs. Some GIS systems automatically resample without warning. Uses may be especially useful with these systems if they are attempting to retain a high degree of spatial integrity in the rasters. So the conversion that they're available tools to converting existing data formats or a raster outputs are listed, and user can easily convert between raster and vector, such as turning a geometry shape file into a raster, and user must choose one attribute field to populate the value of the raster, such as geology unit name. Raster can only store numbers. Numeric fields are converted as is, but text values are assigned arbitrary numeric codes for storage in the raster, and some raster formats place the original text value in raster table for reference. So we may also convert discrete rasters to polygons as long as the number of polygons does not become excessive, and continuous data such as DEM should never be converted to polygons since each pixel is different from its neighborhoods, and it will become a separate polygon. If too many polygons will result from a conversion, the software may be unable to complete the task. So these three methods, we already talked about it. And so we will move on to the analytic masks. So the mask setting is used to specify a polygon feature class or raster that controls which cells will be processed. A mask raster contains no data outside the region of intersect, and all output cells there will be given no data values. If a feature class is used as a mask, then any cells outside the feature class boundary will receive no data values. Okay. So then the tool we use is the extract masks, and we did environmental settings for the raster analysis. So that in using a mask similar to using the clip tool function in vector data. So here is the area outside. So we will extract by masks, and I think I did not a lot for now. So this is the for vector you do clip, and for raster you do is extract by masks. That's the tool, and a lot of students might not remember. Okay, so summary. So raster consists of spatial data stored as individual cells in an array and can represent discrete features or continuous fields of information. Raster have coordinate systems. Must just like other spatial data, many raster calculations are based on distance and area functions. So it is important to store rasters in a projected coordinate system with minimal distortion. And map algebra treats raster as an array of numbers that can be added, multiple, and otherwise manipulated on a cell-by-cell basis. Arithmetic, logical, and Boolean and bitwise operations and functions offer a wide array of operations for analyzing raster and scalars. And raster overlay is generally faster and better incorporates continuous data than vector overlay for suitability analysis. Boolean overlay uses true or false rasters and Boolean operators. Weighted overlay uses reclassification and weights for greater flexibility in modeling suitability. And the distance functions measure distances from a set of objects and can calculate costs and path associated with traveling over a surface. And density functions measures the number of objects occurring within a specified search radius and report in feature per unit area. And raster interpolation estimates a surface based on measurements at isolated locations. And statistical measures can be calculated for rasters based on single cells within a specified neighborhoods or within large irregular zones. Raster can be reclassified and given new values as needed. So resampling occurs automatically when raster with different cells rasters and analyzed together, but can degrade the quality of a data set. And users should attempt to minimize resampling when possible by aligning raster data before analysis. The analysis environment controls certain settings for all new rasters created during a session. These settings include the working directory, the extent and cell size of output rasters, and the analysis masks. Alright, so I will see you next time.